Spring Force Lab by Central Park Tech. Our objective was to uncover Hooke's law using our current knowledge of springs, these are springs, and Newton's second law. We really wanted to find Hooke's law, and our two questions to try to uncover Hooke's law were: how much does the position of the spring change when we add the weights of the spring? And what is the relationship between the stretch and spring force? The procedure for experiment 1, which was when we just took a spring and we added masses of 10, 20, 30, 40, 50, 100, 150, and 200 gram weights onto our spring. And then the procedure for experiment 2 was used using a virtual spring force app, in PhET virtual spring force app, where you add 100, 250, or 50 gram weights to your springs. The results for our live experiment, which is experiment 1, are as follows. We calculated, we didn't need to calculate, but we had the weights of our masses. We calculated the stretch using a ruler, and then we calculated the force using Newton's second law of motion. The results for our virtual experiment, and also helping answer our question, were what were the relationships between force and the stretch. We had the weights, and then we calculated the stretch. We wanted to know what it means, so we graphed the data. This data is graphed from our first experiment, which is the stretch versus the force. The force, as you can see, increases as the stretch increases roughly. And since we had a well-fitting trend line, we wanted to know the equation of it. To do that, we used a device to perform a linear regression. As you can see, there's a positive correlation between the stretch and the force. We used a linear trend line, and it fit the data pretty well. Our R squared was 0.941. If it's 1, that means it fits the data perfectly. Then we wanted to know, what if we were on the moon? What if we on the moon? So data if on the moon, I used the virtual app again, and I used the masses they provided and found the stretch roughly. And I found that the acceleration due to gravity on the surface of the moon is 1.6519 times 412 meters per second squared. If we apply Newton's second law on the moon, we can get the new force just as we did earlier, just using our knowledge of gravitational acceleration on Earth, which is 9.8 meters per second. Then I created a stretch versus force on the moon to see what would happen. We found that our trend line was not as great as it was on Earth. It was only 0.48, showing that there really isn't as much of a positive correlation between stretch and force with springs on the moon. What does this mean? The force is so great on the moon, I believe, that it seems like it would be hard to see a strong correlation between the stretch and the force on the moon. Like I just said, I may be wrong about the acceleration of the moon, but I believe it is 1.6519 times 412 meters per second squared. I hope I'm not, because then that will not really help me, Neil. Anyway, thank you for watching.